This show is an item on the brakes on a car, and a visit to a place where they make glass bottles. First, though, David's going to talk about electricity. I wonder what electricity is anyway.
Next on Acme. Electricity.
Not again.
All right. I'll admit we seem to run across electricity in a lot of items, but that's because it's all around us. In the last 10,000 years or so, electricity's gone from a mystery to a necessity. When you stop and think how important electricity is to our daily lives, it's a little scary. See, there's a little known fact about electricity. It doesn't exist. Well, all right, come on, it sort of exists. Electricity can loosely be defined as a movement of electrons in some medium that will allow that to happen. The movement of electrons can be made to do interesting things. A glance around the house ought to convince you of that. But electricity can't be held in your hand or stored or carried around in a bucket. The most common medium for electricity is metal wire. As electrons flow through the wire and other things, their energy can be converted to other types of energy. The thing that gets very little attention is how the darn electrons get moving in the first place. Anything that can induce those pesky little devils to move is called an electromotive force, EMF. There are 5 different ways to provide the electromotive force, and they're all reversible. 5 different ways. See, that's one of those easy things to remember. There are 5 ways. Now, can I remember all 5 without looking at the props in front of me? Magnetism, chemical change, heat, the piezoelectric effect, and light. The most often used method of generating electromotive force is magnetism. When I wave a magnet near a coil of wire, an electric current's induced in it, as the meter indicates. All the serious electrical power that we use is generated by rotating magnets and coils of wire. The effect is reversible. The electromagnetic effect runs motors, unlocks apartment lobby doors, turns the water on and off in your washing machine, among other things. Electricity and magnetism are inseparable. Following right behind magnetism in the race to provide the electromotive force is chemical change. This little bathtub is made out of brass. This is a piece of magnesium rod. And the tub is full of, don't believe me, salt water. The electromotive force is actually being created by changes taking place in the magnesium. When the magnesium's all gone, no more electromotive force. In a properly designed reaction, the effect is reversible. An external electromotive force applied to the cell will undo the chemical change. Car battery is a good example of a properly designed chemical reaction. The conversion of electron flow to heat is a real common one. Lots of things that perform other conversions also generate heat. Heat's generated in any medium that resists the flow of electricity. That actually qualifies most things. This is a piece of stainless steel wire. The wire that's found in a heater, toaster, stove, or water heater has its resistance tailored to create heat continuously without melting. Electron flow can be converted to heat, and heat can be converted to electron flow with a thing called a thermocouple. If 2 dissimilar metals are joined and heated, a small current flows. The effect's used on gas appliances to signal whether or not the pilot light's lit, and in some thermometers. Now, this effect takes a minute, so through the magic of editing, we're going to cut to a close-up just as the thermocouple gets hot enough. The piezoelectric effect is the least known of the 5 effects, and yet it's everywhere. Some substances will induce electron flow when they're stressed. And by stressed, I mean twisted or whacked. This little thing's out of a barbecue lighter. It gives enough electromotive force to cause a spark to jump a gap. The snap you hear is it's a small hammer stressing the material. A gentler version of this converts wiggles in a record groove to wiggling electric currents. The piezoelectric effect works the other way, too. If a current is made to flow in the material, it will flex. And there are a lot more of these little round discs in your life than you suspect. It's a thin wafer that uses the piezoelectric effect to give off sound. It's in all things that beep. Greeting cards, calculators, computers, coffee pots. probably be in your socks next. The quartz crystal is used in a lot of electronic things to regulate speed. Put into a proper circuit, it can be made to flex and relax at regular intervals. Those intervals depend on the size of the crystal. It regulates watches, clocks, turntables, computers, and keeps all of our radio and TV transmitters on the right wavelengths. A light bulb can be considered to be just a special case of resistance heating. The heater inside gets hot enough to emit visible light. The light-emitting diode emits light directly without creating heat. The light-emitting diode has made it to almost every electric appliance in one way or another. It's very cheap and it lasts forever. Funny thing about them, the light-emitting diode will also cause an electromotive force when light falls on it, but it's very feeble and I can't really demonstrate it. Solar cells are much better at generating EMF. They're used mostly in things orbiting our planet and some calculators. There's even a pack of solar cells you can get that will recharge a dead car battery. Free electricity. Well, solar cells ain't free, let me tell you. But there you have it. 5 different ways to generate an electromotive force and 5 matching ways to use that force. So, what is electricity? I don't know. As a matter of fact, why don't you return your next electric bill unpaid? After all, you're being charged for something that doesn't exist. Here's a container that's made from the cheapest, most abundant substance on Earth. It's sterile, cheap, doesn't contaminate its contents, and it's almost 100% recyclable. It's the glass bottle. Glass dates back to 1500 BC, but it's still a bit of a mystery substance. The encyclopedia calls it an inorganic product of fusion cooled to a rigid condition without crystallization. Michael Faraday characterized it as a solution of different substances. And a ceramics engineer I know calls it a supercooled liquid. And no one has got the explanation for why we can see through it. When glass is made from scratch, the biggest ingredient is sand. At this plant, the biggest ingredient is glass. And only glass. These guys are looking for stuff that will interfere with the rest of the separation process. A magnet at the end of the conveyor catches anything that a magnet will catch, mostly bottle caps. Aluminum caps escape the magnet, but they're fade-awaits. The next step is a cleverly designed crusher that pulverizes the glass but flattens other impurities. Next, the sieve. This machine shakes the mix over a grate. The crushed glass falls through, and the flattened stuff gets directed into a bin. Bye-bye. The cleaned, crushed glass is called cullet. It's inspected. If it doesn't pass, the next step is the first step. It goes through the process again. Brand new clean materials meet up with the cullet here. These big pots are actually scales. Each one's connected to its own balance beam. The fellow that showed us around pointed out that this is much like baking a cake. Measure the ingredients carefully, then throw in the oven. It's a mighty big cake. Tons are mixed at one time. Because of the batch size, the whole process is automated. Measured ingredients are conveyored up to the top floor and mixed in a 3-story bowl. Large buckets on tracks move into position underneath the mixer. A magnet at the bottom of the mixer catches any pesky little pieces of metal that have made it this far. Container glass is made from 73% pure sand, 13% soda ash, 10% limestone, and an assortment of minor ingredients to control its melting characteristics and color. Recycled cullet can be added in large quantities. The train buckets pour the mixture into hoppers that feed the furnaces. Still like making a cake. Mix carefully and bake at 2,800 degrees Fahrenheit. That's real hot, Celsius. The furnaces are monsters. Gas burners at one end fire across the mixture, and air fans on the other side suck the flow towards them. Every 15 minutes, the flow of flame is reversed across the furnace to keep the heat even. A glimpse inside the furnace, glimpse doesn't really do it justice, reminds you of where your mom told you to go if you were bad. At the front end, the powdered mixture is visible as it enters. Further along, the mix is mostly molten, with a few lumps. By the time it exits down a chute, the glass is one homogeneous liquid. The flow out of the furnace is carefully controlled and chopped off in precise amounts. These precisely controlled amounts are called gobs. The gobs drop into chutes and are directed into a 2-stage mold. Molding bottles is a bit like blowing bubble gum. The first stage is poking your tongue into it to make a space for the air that you're going to blow. The two molds look like this. The finished bottle assumes the shape of the inside of the second mold. The top where the cap fits is crimped into shape. An important part of operating the molding machine is swabbing, and oily substance is applied to the molds to prevent the bottles from sticking. Now it's another furnace. The bottles have to be cooled at a controlled rate so they'll be strong but not brittle. The one on the end is being weighed. With a combination of human and automated inspection, the bottles are checked for impurities, thickness, and shape. This machine's making sure that the caps will seal properly. About 10% of the bottles go back to the mixture for another try at the process. This particular plant produces 700 tons of glass bottles a day. From here, they go on to various companies that fill them with everything from baby food to beer. Then it's on to the consumer and back to the plant. I once drove a Jeep that had no brakes whatsoever. Whenever I had to stop for a light, my passenger would hop out and put a brick under the front tire. As a matter of fact, the only accessory that did work was the horn. If you have a vehicle with no brakes, I highly recommend that you have a functional horn. Now, sometimes it's inconvenient to have the passenger hop out all the time, and sometimes you haven't got a passenger. So, for those two reasons, vehicles are equipped with some sort of system to stop the vehicle conveniently from the driver's position. Now, it might take 50 horsepower for 5 seconds to accelerate your car to 50 kilometers per hour. By the Acme School rule number 12 of the universe, it will then take 50 horsepower for 5 seconds to bring it to a stop. Putting that in another fashion, to stop a moving vehicle, you have to get rid of its energy. The braking system of a vehicle is designed to rapidly convert that energy into heat. It does that conversion by a trick first discovered by the caveman: friction. Actually, friction comes into the picture in two different ways. The conversion of forward motion to heat is accomplished by contacting a rotating metal surface with a pad or shoe of softer composition. If the braking system is powerful enough to freeze or lock the rolling wheels, the tires will do that conversion of forward motion to heat. Friction surfaces are mounted on each one of the wheels. Now, to prevent you the necessity of jumping out of the car to activate them, there's a remote control system you can actuate with your foot. In the early days of brakes, the foot force was transmitted to the wheels by steel cables. Steel cables are fraught with problems, most noticeably rust and stretch. There is still a steel brake cable on your car. It's used to activate the parking brake. The serious job of daily braking is left to the science of hydraulics. Officially, hydraulics is the study of movement of water, but we're allowed to apply that name to other fluids as well. Hydraulics relies on two truths. A fluid is not compressible, and a pressure exerted on a fluid will cause the fluid to exert equal pressure in all directions. It's like some people I know. These cutaway models are hydraulic cylinders that are found on a car's braking system. The little one's from one of the wheels. When fluid's forced into it through this hole, the two pistons push out in equal distances with equal amounts of force. Now, some wheel cylinders only have one piston, but they're mounted so that the whole unit can slide freely. And by Newton's first law of brakes, this gives the same effect. The fluid's forced into the wheel cylinders by this one, found under the hood. There are actually two cylinders here with two pistons for safety. Each one operates half of the system. This little piston rod is pushed at both ends by the pressure in both circuits. If the pressure isn't identical, the rod will move a little bit, contact that wire, and light the brake warning light. These passages lead to a reservoir of extra fluid. In the event that the system loses any fluid, it's automatically added. And the brake pedal operates as a lever on this piston rod. Leverage can generate enough force to stop the car, but almost all cars now have an extra device mounted on the master cylinder. It uses the powerful engine vacuum to move a diaphragm as you press the pedal. With this vacuum assist, your big toe can exert enough pressure to stop the vehicle. These are examples of what's found behind the wheels on a car or a small truck. The drum brake was the commonest type of brake assembly until the 1970s. Drum brakes all have two friction devices called shoes, but the shoes can have different functions depending on the layout. Larger vehicles use a layout like this called servo brakes. When the shoes are pushed outwards by the hydraulic cylinder to contact the drum, they attempt to rotate with it. Servo brakes have one large shoe and one small one. The way the shoes are anchored gives them a neat twist. When the small one contacts the drum, it's free to rotate a bit. This rotation pushes at the end of the bigger shoe, which can't rotate because the other end of it is anchored. The effect of all this is that the smaller shoe forces the larger shoe to press harder on the drum, aiding the friction. Servo brakes work when the vehicle's reversing, but then the larger shoe is forcing the smaller shoe into the drum. Brakes on smaller cars use two equal-sized shoes that are self-pushing. You can get an idea of how a shoe wedges itself into the drum by moving one hand over the other like this. In this type of brake, only one shoe really does the braking, depending on which way the drum's turning. The extra parts here are to adjust the position of the shoes as the friction surface wears, and to allow connection to a steel cable that can lock the brakes on for parking. there's a good chance that drum brakes still exist only because of the ease of making that parking brake linkage work, because there's a much better brake assembly. If you ever noticed the way the front of a car dips when the brakes are applied, you already know something important about the car's braking system. The front brakes do most of the work. The self-wedging action of the drum brake is good, but it means the shoes need spring action to return them to rest, and because of that, they need some means of adjustment as the shoes wear down. Also on their bad side, the outward push on the drum, coupled with the heat generated, can distort the shape of the drum, and the drum collects dust and grit of all kinds. This is a disc brake. It works like this. The disc is exposed to the air, and that helps keep it clean and dissipate heat. As well, friction pads push equally on both sides of the rotating surface, so there's less chance for distortion. The unit that pushes the pads contains a hydraulic cylinder that pushes only on one of the pads, but the whole works is free to slide a bit, so an equal force gets centered on that rotor. Now, since there's no self-wedging action, no springs are required. When there's no pressure on the hydraulic piston, the pads ride right alongside the rotor. As the pads wear, more hydraulic fluid fills up behind the piston to take up the slack. In a car with disc brakes, you'll notice fluid slowly disappearing from the fluid reservoir as the pads wear. Here's a disc pad. This little tab has an interesting function. When the pads get thin enough to require replacement, it contacts the rotor and makes a screeching noise. In any event, if you hear any odd noises from the braking system, it's probably time to have it checked. Either that or make sure you always have a passenger with a brick.